Hello viewers, welcome to the lecture on companion form. In this lecture, we shall see an important result which relates companion form and controllability of a linear system. So, to start with, let us see what a companion form means. Companion form. So, let C be a matrix of order n given by 0 1 0 0 0 0 1 minus alpha n minus alpha n minus 1 minus alpha 1. So, here the off diagonal elements are 1 and the last row can be 0 or non-zero elements. And let us consider matrix D, which is a column matrix like this, and let y of t belongs to Rn and u of t belongs to R for each value of t. Then the control system y dot, that is dy by dt equal to cy plus du is called a companion form. So, any control system which can be written in this particular form is called a companion form of that control system. So, let us see from where we obtain the companion form. So, for that, let us consider the differential equation of order n. Plus a2 d n minus 2 y d n minus 2 etc. plus a n into y of t equal to some function v of t. So, it is a nth order differential equation. Here a, I are constants, nth order equation with constant coefficient. Now, if you convert this nth order equation into n first order equation by substituting, so let us take y is equal to y1 and dy by dt equal to y2 etc. dn minus 1 by dt n minus 1 equal to yn. So, then we will get the derivative y1 dot equal to y2, y2 dot equal to y3, here it is yn, sorry, and yn dot, that is the nth derivative of y, that is equal to the expression. If you take all this to the right hand side, we will get a n by a 0 into y1 minus a n minus 1 by a 0 into y2 etc. minus a n by a 0 yn plus v of t by a 0. So, we get this expression. So, if you substitute a I by a 0 as alpha I and v of t by a 0 equal to u of t, then we get the companion form. Then this system is written in the form of companion form. Then the above system is of the form y dot equal to Cy plus du, where y is the vector y1 etc. yn, and C and D are defined in the previous slide. So, from an nth order differential equation we can always obtain the companion form like this. Now, we will see that the controllability of the companion form. So, if we consider the system y dot equal to Cy plus du, then the system is controllable if and only if the rank of the matrix D, CD, C square D etc. C n minus 1 D. If it is equal to n, this is the Kalman condition. Then the system is controllable. But it is very clear that the rank of first column is D, that is 0 0 etc. 1, and if you multiply C into D, where C is given by the previous slide, if you multiply C into D, we will get the last but one element is 1 and the last element will be minus alpha 1. So, we will get the second one is 0 0 1 and minus alpha 1 will come. Similarly, the third one will be 1 and some two non-zero elements, 0 or non-zero elements are there, and finally we will get 1 and various elements. Okay. So, it is very clear that the determinant of this matrix is non-zero, that is 1, and therefore, the rank equal to n. So, any system which is in the companion form, it is always controllable. So, you can say that if the differential equation is considered as a control system where the right hand side is considered as control, then it is always controllable for any desired y dot etc. up to the nth derivative. We will obtain a particular control to steer the system. So, now we will come to the general theorem. The question is, if we consider general system, if we consider the system of the form, let us say x dot dx by dt equal to Ax plus Bu, where A is any n cross n matrix and B is n cross 1 matrix. It may not be in the companion form. So, the question is, can we convert it into a companion form? Convert this equation to, let us say, into the companion form. So, let us call this as equation 1, companion form 1. So, this is the main result, that is, if the system 2 is controllable, the result is, the theorem says that the system 2 can be converted into the companion form 1 if and only if the system 2 is controllable. In other words, if and only if the rank of, that is, the rank of the matrix, here the column matrix B, A B, A square B, etc., A power n minus 1 B equal to n. So, here we consider A to be n cross n, B is a column vector only. Okay. We do not consider this result for any general B, that is n cross m matrix B, that we will consider in the later lectures. So, this matrix is a n cross n matrix. So, it should be invertible. The meaning is, so the how to convert the system into this particular form, it is using a transformation. So, let us consider the transformation. Y is equal to Tx. Here x is a column vector, y is column vector belonging to Rn, and T is n cross n non-singular matrix. Let us say T is any non-singular matrix, just we take a transformation. Now, given the system is x dot equal to Ax plus Bu. If we multiply both sides with T, Tx dot equal to Tax plus Tb into U. And if T is invertible, we have x is equal to T inverse y. So, that implies Tx dot equal to Ta, and x can be replaced with T inverse of y plus Tbu. And because T is a constant matrix, we assume the derivative of y is same as T into x dot. So, this implies that y dot equal to T A T inverse into y plus T B into U matrix. So, if this T A T inverse is in the form of C and T B is in the form of D, then we obtain the transformation T which convert it into the companion form. So, we obtain the companion form if T A T inverse is the form of C and T into B is in the form of the D matrix. So, if it happens, then the result is true. So, what we will prove here is this particular thing can happen if and only if the system is controllable, that this one rank of B, A B, A square B, etc., equal to n, then we will be able to find a matrix T satisfying the last condition like this. So, we will first prove the necessary condition. So, the necessary condition is if the matrix, so necessary condition, if the system is, if the system 2 can be converted into the companion form. Companion form 1, then we have to prove that rank of B, A, B, etc. A power n minus 1 B is n. So, it means if it can be converted into companion form, then the system is controllable. So, it is given that x dot equal to A x plus B u is converted into y dot equal to C y plus d u, where C is T A T inverse and D is T into B. So, this is given to us. Now, we have to prove that the rank of this matrix is n. So, now it is known that the companion form is always controllable. Since the companion form is controllable, so we get the rank of D, C, D, etc. that is equal to rank equal to n. So, now we have to prove the other one. If you call this as 3 and this as 4, from 4 we have to prove 3. So, what we do, directly substitute the D value. So, this implies that rank of D is given by T into B and C is given by T A T inverse into D, that is T into B, and C square means T A square T inverse and D is T into B, etc. and C power n minus 1 T A power n minus 1 T inverse D is T into B. So, this matrix has rank n, it is given by 4. So, this implies that rank of T B and T inverse into T becomes identity. So, we will get T A B, third one will become T A square B, etc. T A power n minus 1 into the rank equal to n. So, now T is the common n cross n matrix in the left side of all the products. So, we will get that the rank of the matrix T multiplied by the remaining matrix B, A B, A square B, A power n minus 1 B, that is equal to n. Now, rank of this is a product of two matrix, T is one matrix and the remaining is the other matrix, n cross n matrices. Already we know that rank of T equal to n. So, if the rank of the other matrix, if it is less than n, then the product of these two matrix, the rank will become less than n. So, it implies that the rank of B, A, B, etc. A power n minus 1 equal to n, since rank of T equal to n. So, it proves that the condition is necessary, that is, if the system is converted into companion form, then the system has to be controllable. That is proved here as the necessary condition. Now, we can prove the sufficient condition. So, if the rank of the matrix is n, if the system is controllable, then we have to prove that then system 2, that is x dot equal to x plus bu, can be converted into system 1 in a companion form, or in other words we will get a matrix we can get a non-singular matrix T such that T A T inverse equal to C and T B equal to D matrix. So, we have to show that this is possible. So, now making use of the rank condition, we can construct the matrix T. Now, we can construct the matrix T in the following way. So, let us take T equal to, the first row is a unknown vector alpha, alpha 1, alpha 2 etc., alpha n is the first row, and the second row is alpha times A, and alpha times alpha is a row vector, A is a n cross n matrix. So, the product will be a row vector, that is the second one. Similarly, third, fourth etc., all of them are alpha times A n minus 1 is the last vector. Okay. So, we take a matrix T in this particular form. Now, if you are able to find this alpha vector, then it is clear that we can get the entire matrix T. So, let us see how to construct this alpha matrix. So, first it is given that if at all there exists a matrix T, then T into B should be equal to D. So, okay, if the matrix exists, then T into B should be equal to D. So, this implies that alpha into the B matrix, that is the first element. If you multiply T into B, it will be single element. Okay. The first element is alpha into B, it is one element, then alpha into AB is another element, alpha A power n minus 1 B is the last element. So, it is n cross 1 matrix, but this should be equal to 0 0 0 1 because it is equal to D. So, this implies alpha into B is 0, alpha into AB is 0 etc., the last one is like this. So, this implies alpha times B. So, if you write the B as the first column, then AB as the second column, A power n minus 1 B, that is the nth column. Take alpha common outside, so we will get all the entries. Alpha into B, that is the first element is 0, alpha AB if you multiply, the second element is 0, the last element is 1 here. So, we get the expression like this. So, if we take this as, let us say, alpha into the matrix U, let us say the Kalman matrix B, A, B, etc., if you denote it by the matrix U. So, alpha into U is nothing but 0, 0, 1 matrix. So, this gives, because the rank is n, it is invertible matrix, U is invertible, we get alpha equal to 0, 0, 1 multiplied by U inverse. So, it is the unique solution of the problem, the algebraic system of equation. Because U is invertible, we get a unique solution alpha. By substituting that alpha in the T matrix, we get the n cross n T matrix. Now, we have to check whether T A T inverse is in the form of C or not. We got T B equal to D, we have already solved. Now, if you put it here, will it give a matrix in the form of C? So, now to check, if T A T inverse equal to the form of C matrix. So, that can be easily proved here. So, let T is already given, that is alpha first row, alpha into A, etc., alpha A power n minus 1, and let us assume T inverse. If you find, because we do not know this alpha value exactly, so we just give a notation here. The first column is S1, the second column is S2, the nth column is Sn, and T into T inverse will give identity. So, that implies, if you multiply T and T inverse, the first element is alpha into S1, the second element is alpha into S2, the first row into second column, etc., alpha into Sn. Second row first column will give alpha A S1, and second into second alpha A S2, etc., alpha A Sn, and the last one is alpha A power n minus 1 into S1, alpha A power n minus 1 S2. So, this is a n cross n matrix, which is the identity matrix, okay. 1 0 0 0 1 0. So, we can easily compare this, alpha into S1 has to be 1 and alpha into S2 has to be 0, etc. This comparison is there. Now, if you take T A T inverse, that is nothing but T A multiplied by S1 S2, etc., isn't it? First column, S2 is second column, Sn is the nth column. So, we will get the expression like this. The first element is T, the first one, okay, again we have to write alpha times A. The first element is alpha is the first row multiplied by this matrix will give the first row. The second row is alpha A multiplied by A, that is alpha A square, etc., alpha A power n minus 1 is the last row multiplied by A, that is alpha A power n, okay, that is. So, this is T into A, multiplied by the T inverse S1 S2 Sn. So, it can be easily seen that the first row into the first column, that is alpha A into S1, that is the first element, okay, that is here, alpha A S1 is 0. So, what we observe here is the first row whatever we calculate, that will come out to be the second row of the identity element. Similarly, the second row alpha A square S1 etc. will come out as the third row of the identity matrix. So, ultimately the first row of T A T inverse is the second row of the identity matrix. The second row of T A T inverse is the third row of the identity matrix, etc. So, till the n minus 1 we will get like this, but the last one we do not know what it is, because there is no comparison in the equation. So, the last row can be whether it is a 0 value or non-zero value, we do not know, but it is in the companion form, it is in the form of the C matrix. So, if you calculate T using this expression alpha equal to 0 0 1 into U inverse and substitute it in the T matrix, we will obtain T, and from that T, if you calculate T A T inverse, we will get a C matrix in this form. So, we will be able to, and this construction is unique, T is a unique construction because of the equation here alpha into U equal to this expression. So, we get it in a unique manner. So, this proves the sufficient condition that the system has to be controllable for a conversion of the companion. Okay. Now, we will quickly see the following example. If A is the matrix, let us say 2 1 1 2, and B is the matrix, let us take any vector like this, then it is controllable. The system x dot equal to Ax plus Bu is controllable because the rank of B is this and AB is 7 8. A into B will give this thing, this is equal to 2. So, this implies x dot equal to Ax plus Bu is controllable matrix, is not it. Now, can we convert it into the companion form? So, we have to find the value of alpha from the equation alpha equal to 0 1, because it is a 2 by 2 matrix, into the inverse of the matrix 2 3 7 8, the inverse. So, once we get the value of alpha, so we can see that alpha value is given by 3 by 5 and minus 2 by 5. So, we can calculate like this, and so this implies T is the first row is alpha, the second row is alpha into A. So, if you calculate this expression, we will get 3 by 5 minus 2 by 5 is the first row, second row will be 4 by 5 and minus 1 by 5 is the T matrix. Then we can obtain this T A T inverse. If you multiply, we will get the C matrix and T into B. we will get 0 1 in the companion form of the expression. So, companion form is a very important form in the control system. We will see in the next lecture the application of the companion form in the feedback control of a linear control system. Thank you.